Is gravity a fundamental force or a cosmic mirage? This is the central puzzle of quantum gravity, the greatest unsolved problem in modern physics. For a century, our two most powerful descriptions of reality have been locked in a silent war. Einstein's theory of general relativity paints a beautiful picture of a smooth, curving spacetime, explaining the dance of planets and the pull of black holes. Yet quantum mechanics reveals a frantic, probabilistic underworld where particles pop in and out of existence. These two theories work perfectly in their own domains, but when they meet, the math explodes into nonsense. The quest to unite them into a single, coherent framework is the ultimate scientific challenge, and its solution will rewrite our understanding of everything from the birth of the cosmos to the nature of time itself. By the end of this journey, you will have explored 30 of the most profound and mind-bending theories that attempt to crack this code. We will see how some ideas suggest our universe has hidden dimensions, while others propose that space and time are not smooth but made of tiny, discrete loops. Could spacetime be a hologram, a projection from a distant, two-dimensional surface? What if gravity is not a force at all, but simply a consequence of chaos and information? We are about to venture from the established edges of string theory to the wild frontiers of emergent reality. Which of these ideas do you feel could be the key to unlocking the universe? One of the most celebrated contenders in this grand quest is string theory. It proposes a radical shift in our understanding of reality's building blocks. Forget infinitesimal points. The seeds of everything are unimaginably tiny, vibrating loops of energy. Think of a violin string. Pluck it one way and it produces a specific musical note. Pluck it differently and you get another. In string theory, the distinct vibrational patterns of these fundamental strings are what create the entire particle zoo. One specific resonance might give you an electron, another a quark, and a particularly special vibration would produce the graviton, the hypothetical particle that carries the gravitational force. This elegant idea naturally weaves gravity into the quantum tapestry, offering a potential path to peace between Einstein's cosmos and the quantum world. Yet this beautiful solution comes with a breathtaking cost: extra dimensions of space. For the math to work, our familiar 4 dimensions are not enough. The most common versions of string theory require 10 or 11 dimensions in total. These extra dimensions are thought to be curled up or compactified into shapes so incredibly small that we cannot perceive them, explaining why our spacetime appears smooth and continuous on large scales despite the underlying quantum frenzy. Over the years, physicists have discovered several distinct versions of this theory, like Type 1, Type 2a, Type 2b, and heterotic strings, each with its own unique mathematical structure. While the theoretical elegance is profound, string theory faces a monumental obstacle. The energy levels required to probe these tiny strings or detect extra dimensions are far beyond the reach of any particle accelerator we can build. For now, it remains a magnificent, unverified symphony of mathematics, a potential key to the universe that we cannot yet turn in the lock. While string theory weaves gravity from tiny vibrating strings, another powerful idea suggests the problem is not with the forces, but with the very stage they perform upon. This is loop quantum gravity, a theory that dares to chop spacetime itself into pieces. It proposes that the smooth, continuous fabric described by Einstein is actually an illusion, a macroscopic average of a reality woven from a billion tiny, indivisible loops. Picture the universe not as a smooth sheet, but as a vast, dynamic web of interconnected threads. This is the spin network, a structure where each link represents a fundamental quanta of space, a single loop carrying a tiny unit of area. The places where these loops intersect, the nodes of the network, represent the smallest possible volumes. There is no such thing as an infinitely small point in this theory. Space comes in discrete, finite chunks. And just as a movie is made of individual frames, the flow of time emerges from the evolution of this network. As the spin network changes, it creates a complex foaming structure known as spin foam, a history of spacetime itself. This background-independent approach is a stark contrast to string theory. Loop quantum gravity does not require a pre-existing spacetime for its strings to vibrate within. It builds the stage and the actors from the same fundamental stuff. This radical rethinking leads to profound consequences. It naturally resolves the terrifying infinities of singularities. Inside a black hole, or at the moment of the Big Bang, general relativity predicts that density and curvature become infinite. But in loop quantum gravity, you simply run out of space. You cannot pack matter into a volume smaller than the smallest possible node in the spin network. This means the Big Bang was not a true singularity, but a great bounce from a previous universe, and black holes have a finite, calculable entropy. The cosmos becomes a tapestry of finite threads, forever weaving itself into existence, one tiny loop at a time. But what if the universe is built like a digital mosaic, assembled from a cosmic box of Legos? Causal dynamical triangulations offers precisely this vision, constructing reality from the simplest possible building blocks. Imagine you have a colossal supply of tiny, multifaceted shapes, the most basic geometric forms possible. In this theory, these are the fundamental units, the atoms of spacetime itself. The rules for snapping them together are incredibly strict, governed by causality. This means every connection must respect the flow of time, ensuring that cause always precedes effect in your miniature universe. You cannot just glue pieces together randomly. Each triangular piece must connect in a way that creates a consistent, unbroken arrow of time from one moment to the next. From a distance, this vast, churning assembly of geometric shapes looks random and chaotic. Yet something miraculous happens as you zoom out. All those jagged, microscopic edges begin to smooth out. The chaotic jumble of triangles self-organizes, giving rise to the familiar, smooth, four-dimensional spacetime we experience. This is dimensional emergence in action. The theory does not assume we live in 4 dimensions. It shows how those 4 dimensions can be the natural, large-scale consequence of these simple building blocks following causal rules. This is a huge success. It demonstrates mathematically how a classical, orderly universe can spontaneously arise from a frothing quantum foundation. Unlike some approaches that rely on approximations, causal dynamical triangulations is non-perturbative. It tackles the entire problem of quantum gravity head-on without trying to build it as a small correction to an existing theory. It starts from scratch from a box of geometric pieces and builds a cosmos that looks remarkably like our own, one tiny triangle at a time. Sometimes the most elegant solution is to fix the tool, not build a new one. Asymptotic safety in quantum gravity makes this bold claim. It argues that we may not need radical new dimensions or discrete spacetime atoms to solve the gravity puzzle. Instead, the theory of general relativity itself could be perfectly quantum, if only we view it from the right angle. The problem, as we know, is that the math of quantizing gravity breaks down at incredibly high energies, producing infinite, nonsensical answers. This is where a powerful concept from quantum field theory comes into play, the renormalization group flow. Think of this as a cosmic tuning dial for the laws of physics. As you change the energy scale you are examining, the effective strength of forces can shift. For a theory to be well-behaved or renormalizable, its parameters must settle into finite values no matter how high you turn the energy dial. For decades, gravity failed this test. Its strength seemed to spiral out of control. Asymptotic safety proposes a brilliant loophole. What if gravity's flow through this cosmic parameter space does not go wild, but instead is drawn toward a special anchor point, an ultraviolet fixed point? At this unique point, the theory's behavior becomes predictable and finite again, even at the highest imaginable energies. It is like a river that seems to rage uncontrollably, but if you follow it all the way to its source, you find it emerges from a calm, stable spring. If gravity is asymptotically safe, then the familiar equations of general relativity are not wrong, they are just incomplete. They are the low-energy manifestation of a deeper, perfectly consistent quantum theory. This would be a monumental achievement, allowing physicists to quantize gravity using the established toolbox of quantum field theory, the same framework that so successfully describes the other three fundamental forces. Computational studies and complex lattice simulations have provided tantalizing hints that such a fixed point might indeed exist. The numbers suggest that spacetime, when probed at its most fundamental level, might not be a foreign landscape after all, but a familiar territory waiting for us to learn its true quantum rules. What if gravity is not a force at all, but a cosmic illusion? This is the startling proposal of Eric Verland, who suggests that gravity is emergent, a side effect of a much deeper principle, the drive towards disorder. We are familiar with entropy in everyday life. A drop of ink spreads through a glass of water, ice cubes melt in a warm drink, all moving from order to disorder. This tendency is so powerful it can create what looks like a force. Think of a simple polymer, a long chain of molecules coiled in a messy ball. If you try to pull it straight, you are forcing it into a very ordered, low-entropy state. The chain will resist, not because of some fundamental repulsion force, but because the universe prefers mess. It fights back with an effective force, a pull back towards its high-entropy, tangled state. Verland applies this logic to the fabric of space itself. He proposes that the vacuum of space is not empty, but is filled with fundamental bits of information, like the zeros and ones of the cosmic code. When you place a massive object like a star into this vacuum, it disrupts the information in its surroundings. The natural tendency of this system is to regain its state of maximum entropy, and this relentless drive to re-establish disorder manifests as what we perceive as gravity. The star is not pulling on planets with a mysterious force. The space around it is simply pushing everything towards the configuration of highest entropy. The mathematics of this process are breathtaking. Starting from only these basic principles of information and entropy, Verland's equations naturally reproduce Newton's law of universal gravitation. With a bit more work, they even generate the full geometry of Einstein's general relativity. Gravity, the force that has guided cosmic evolution for billions of years, emerges not as a fundamental actor, but as a statistical tendency, a thermodynamic mirage. This radical shift in perspective offers a stunning solution to physics' greatest mysteries. Dark matter, the invisible substance thought to hold galaxies together, might not be a type of particle. Instead, the unexpected rotation of galaxies could be a direct result of this entropic gravity, a subtle effect that becomes significant on vast cosmic scales. Similarly, the accelerated expansion of the universe, which we attribute to dark energy, could simply be the universe continuing its relentless journey towards its state of ultimate disorder. If Verland is correct, then we are not being pulled by the stars, but pushed by the hidden structure of information itself. This drive toward disorder gives gravity an almost ghostly quality, a force born from statistics rather than substance. But what if we strip reality down even further to its barest logical bones? Causal set theory does exactly that, proposing a universe built not from stuff but from pure relationship. The fundamental ingredients are not particles or strings, but simple, indivisible events. Think of each event as a single grain of cosmic sand. These grains are not scattered randomly, they are connected by a single, overriding principle, cause and effect. One event can influence another, creating a vast web of relationships known as a partial order. This network of causes is the causal set, the complete history of everything that has ever happened or ever will. In this view, spacetime is not a primary entity, it is a secondary, approximate concept. The smooth, four-dimensional continuum we experience is a kind of blurry, large-scale average of this underlying, discrete network of causal links. It is similar to how a smooth, continuous photograph emerges from a finite collection of discrete pixels. The more grains you have, the smoother the emergent picture becomes. The incredible power of this idea is that it derives the geometry of the universe, the very distances and durations of general relativity, solely from the causal relationships between events. If one event can influence another, then they are time-like separated, and the number of intervening grains in the network defines the proper time between them. If no signal can travel between two events, they are space-like separated. From the simple, granular structure of cause and effect, the full richness of spacetime geometry is reborn. This approach offers an incredibly elegant escape from the problem of singularities. In a place like the Big Bang, where general relativity predicts an infinitely dense point, the causal set simply has a finite number of elements. There is no infinite density because there is no continuum to become infinitely curved. There are only a finite number of grains at the beginning. The universe starts not with a bang, but with a first cause, a single seed event from which the entire cosmic web unfurls. Here, causality is not just a rule within the universe, it is the universe itself, a timeless order of events waiting for us to mistake its connections for a flowing river of time. From the stark simplicity of causal sets, we arrive at a universe where geometry itself becomes uncertain. Non-commutative geometry proposes that the very coordinates of space and time lose their classical certainty at the smallest scales. In our everyday world, it does not matter if you measure a room's length before its width, you will get the same result. The numbers commute, but in the quantum realm, this order suddenly matters profoundly. The most famous example is the position and momentum of a particle, where measuring one fundamentally disturbs the other. Now, apply this quantum rule to the fabric of spacetime. If the coordinates of an event, its x, y, z, and even t, do not commute, then the precise location of a point becomes a meaningless concept. You cannot pin reality down to a single, infinitesimal spot. Instead, spacetime develops an inherent fuzziness, a fundamental graininess where points are smeared out into a kind of quantum cloud. This is not just a blurry photograph, it is a radical rewriting of geometry at the Planck scale. The smooth, continuous stage of Einstein's universe is replaced by a foaming, uncertain quantum landscape where the very concept of here and there becomes fluid. This mathematical framework is incredibly powerful because it can naturally incorporate the entire standard model of particle physics. The different particles and forces, with all their strange properties, emerge from the specific ways that this fuzzy spacetime fails to commute. It is as if the forces of nature are not inhabitants of space, but are the direct expression of its quantum geometric melody. This leads to subtle but profound modifications of Einstein's field equations, predictions that could one day be tested as our telescopes and detectors become more sensitive. Most importantly, this inherent fuzziness provides a natural cure for the infinities that plague general relativity. In a black hole singularity, classical theory predicts a point of infinite density. But in non-commutative geometry, there is a minimal length scale built directly into the universe's architecture. You cannot compress matter into a volume smaller than this fundamental pixel of reality. The terrifying singularity is replaced by a dense but finite quantum state. The Big Bang was not an infinitely hot, infinitely dense beginning, but a transition from a previous cosmic phase, a moment of maximum compression where the quantum nature of spacetime prevented true infinity. The universe, in this view, is not built on a fixed grid, but sings with a fundamental uncertainty, a geometric hum that underpins all of existence. This geometric uncertainty hints at a far deeper strangeness, a possibility that our entire three-dimensional world is a magnificent illusion. The holographic principle declares that all the information needed to describe every particle, every force, and every event within a volume of space can be perfectly encoded on its two-dimensional boundary. Imagine the universe as a cosmic prison cell. You and everything inside it are not truly three-dimensional entities, but intricate patterns of information painted like a tattoo on the distant two-dimensional walls. This is not science fiction, it is a serious idea born from the thermodynamics of black holes. When matter falls into a black hole, it seems to vanish, but its information cannot be truly destroyed. Physicists discovered that the maximum amount of information a region of space can contain is not proportional to its volume, but to the area of its surface. A three-dimensional box does not hold information like a full storage container, but more like the surface of a soap bubble, with all its complexity shimmering on its skin. This realization reduces the fundamental degrees of freedom in the universe dramatically, simplifying the daunting task of quantum gravity by effectively removing one entire dimension from the problem. The most concrete and powerful evidence for this principle comes from a specific mathematical discovery known as the AD-SCFT correspondence. It establishes a perfect duality, a cosmic dictionary between two seemingly unrelated worlds. On one side is a theory of gravity operating in a special type of space called anti-de Sitter space, which has a distinct boundary. On the other side is a conformal field theory, a quantum theory without any gravity at all, that lives exclusively on that lower dimensional boundary. These two theories are completely equivalent. Every single event, every gravitational interaction happening in the bulk of the higher dimensional space has a perfect mirror description as a complex dance of quantum particles on the boundary. A star collapsing into a black hole in the gravity theory is exactly the same as a specific state of a hot, dense plasma in the quantum field theory. This is not just a vague analogy, it is a precise mathematical equivalence. The implications shatter our classical intuition. Locality, the cherished idea that objects are directly influenced only by their immediate surroundings, may be an emergent property, not a fundamental one. In the holographic description, two particles interacting inside the universe might be described by processes that are instantly connected across the entire boundary surface. What we perceive as a local force of gravity could be the result of a vast, non-local computation happening on the edge of reality. If the holographic principle is correct, then our rich, three-dimensional experience of the world, the feeling of depth and substance, is a magnificent projection, a cosmic sleight of hand performed by a universe that is fundamentally simpler, flatter, and infinitely more connected than it appears. This idea that gravity is an emergent phenomenon takes us far beyond any single theory, into a profound reimagining of cosmic foundations. The radical suggestion is that gravity, and even the stage of spacetime it plays out upon, are not fundamental ingredients of the universe. They are collective illusions, large-scale behaviors that arise from countless microscopic interactions that know nothing of gravity or geometry. Think of a flowing river. The water itself is just a vast collection of individual H2O molecules, each bouncing and jostling against its neighbors. None of these molecules possesses the concept of a whirlpool or a current. Yet, when you zoom out, these collective dynamics give rise to the smooth, powerful flow of fluid dynamics. Emergent gravity proposes that spacetime is like that river. Its smooth curvature and the force we call gravity are the large-scale consequences of something else entirely, a hidden quantum underworld. This is a true paradigm shift. The central conflict between general relativity and quantum mechanics might be based on a false premise. We have been trying to quantize gravity, to force it into the quantum framework, but what if gravity was never a fundamental force that needed quantizing in the first place? What if it simply emerges naturally and inevitably when a vast number of non-gravitational quantum parts organize themselves? Various models explore what these underlying parts could be. Some are inspired by condensed matter physics, drawing analogies to exotic phases of matter. In this view, the vacuum of space is not empty, but a kind of cosmic superfluid or a Bose-Einstein condensate. The ripples and excitations within this quantum medium could manifest as particles and forces, with gravity being a particular kind of collective vibration, much like sound emerging from the coordinated motion of atoms in air. Other approaches are rooted in quantum information theory, where the fundamental stuff of reality is not matter or energy, but information itself. In these models, spacetime geometry is literally built from quantum entanglement. The connection between two entangled particles, that spooky action at a distance, is not just a feature of space, it is what creates space. The distance between 2 points, the very fabric that separates them, is woven from the web of entanglement between the underlying quantum bits. More entanglement creates a shorter, tighter geometric connection, like a quantum thread pulling points closer together. In this breathtaking picture, the force of gravity we feel could be a direct consequence of the universe constantly working to maximize the entanglement between its fundamental components. A massive object like a star would be a region of incredibly complex entanglement, and its gravitational pull is just the tendency of other systems to become entangled with it to share information. This resolves the conflict at its core. There is no quantum theory of gravity because gravity is not a quantum actor, it is a thermodynamic collective outcome. The search for a graviton, the hypothetical quantum particle of gravity, might be like searching for the molecule of a whirlpool. It is a misidentification of the phenomenon's true nature. The smooth spacetime of Einstein and the frantic quantum world are not two opposing kingdoms. They are simply different levels of description of a single, deeply interconnected reality. Supersymmetry offers a beautiful symmetry to the particle world, proposing that every known particle has a hidden, super-powered twin. The matter particles, called fermions, would be paired with force-carrying bosons and vice versa. This elegant partnership could solve several deep puzzles in physics, stabilizing the Higgs boson's mass and providing a natural candidate for the universe's dark matter. When this powerful symmetry is applied not just to particles but to the fabric of spacetime itself, we get supergravity. This theory seamlessly weaves the principles of supersymmetry into Einstein's general relativity. The result is a gravitational force that is richer and more complex. The graviton, the quantum of gravity, gains a superpartner of its own, a particle named the gravitino. This fermionic twin would be a bizarre and powerful entity, a mix of spin characteristics that links the force of gravity directly to the world of matter in a completely new way. The most captivating version of this theory emerges in 11 dimensions. Here, supergravity achieves a remarkable mathematical purity and uniqueness, presenting itself as a powerful candidate for a unified theory of everything. For a time, it was seen as a potential successor to string theory, a more economical framework that might accomplish the same grand goal. While string theory ultimately absorbed it as a crucial component, supergravity remains profoundly important as the low-energy limit of string theories. It describes how the universe behaves at energies we can somewhat comprehend before the full, dizzying structure of strings becomes apparent. Its power is not just theoretical. Supergravity has provided deep insights into the quantum properties of black holes, allowing physicists to calculate their entropy with stunning precision from first principles. This successful marriage of gravity and supersymmetry shows us a universe where the forces and matter are not separate families, but two sides of the same cosmic coin, dancing together in a hidden, higher dimensional space. While the holographic universe suggests our world is a projected image, another path abandons the stage of spacetime entirely. Roger Penrose's twistor theory proposes a reality built from something far more abstract and beautiful. Its fundamental ingredients are not points in space or vibrating strings, but twistors, complex geometric objects that exist in their own multidimensional realm. In this radical vision, the familiar concepts of here and there, of now and then, are not the starting point. They are secondary, derived from the intricate interweaving of these twisters. Think of a vast cosmic tapestry. Instead of seeing the final picture, the space-time we live in twister theory asks us to look at the individual threads. Each twister is like a single, luminous thread carrying information about both a point in space-time and the momentum of a particle. It fuses the concepts of location and motion into one fundamental entity. When these threads cross and interact in the twister space, they weave the fabric of our physical reality. A point in our four-dimensional world is not a primary building block, but the result, the shadow, of a specific collection of intersecting twisters. This background-independent approach is profound. It does not assume a pre-existing spacetime for things to happen within. It builds spacetime itself from these more primitive relationships. This has led to one of twister theory's most spectacular successes, simplifying the fiendishly complex mathematics of particle scattering. When physicists calculate the probabilities of particles colliding and rebounding in powerful accelerators, the math can involve thousands of pages of dense calculations. Twister methods have shown that these same amplitudes can often be described with breathtaking elegance, sometimes reducing a mountain of algebra to a single, graceful geometric picture. The theory reveals a hidden simplicity underlying the apparent chaos of particle interactions. Its connections to other great ideas are deep. Twister geometry shares mathematical harmonies with the concepts of string theory, suggesting they might be different perspectives on the same underlying truth. While still a developing framework, twister theory continues to inspire physicists as a potentially more direct and elegant route to a unified theory, a path where the rigid geometry of Einstein's universe blossoms organically from a deeper, more fluid, and more beautiful foundation. If twister theory weaves space from abstract threads, group field theory builds it from quantum bubbles of geometry. This framework is a second quantized version of loop quantum gravity, a step that transforms the entire picture. In standard quantum field theory, we start with a vacuum and create particles like electrons or photons by exciting fields. Group field theory applies this powerful logic to the fabric of space itself. Its fundamental quanta are not particles of matter, but elementary chunks of space, the same indivisible atoms of geometry found in spin networks. Here, you do not start with a universe, you start with a void, and then you create space. A quantum of space is like a single bubble. The theory's fields create these bubbles, each one carrying a tiny bit of geometric information, a potential building block for reality. The true magic unfolds in their interactions. In particle physics, when particles interact, they scatter or decay. When these quanta of space interact, they do something far more profound. They fuse together. They combine to form larger, more complex structures, literally building up the geometry of space-time from the bottom up. The mathematics governing this cosmic construction is breathtakingly elegant. The Feynman diagrams of this theory are not simple lines showing particle paths. They are full-blown spin networks and simplicial complexes. Each diagram is a complete, if miniature, universe in its own right, a specific history of how elementary quanta of space connected and interacted to form a geometric structure. Think of it like a quantum Lego set where the instructions themselves generate the final model, a dynamic process where space is constantly being assembled and disassembled. This makes group field theory profoundly background independent. It does not assume a pre-existing stage. The stage is the final, large-scale result of this relentless quantum gravitational activity. Its ultimate ambition is staggering: to provide a complete and self-contained theory of quantum gravity from which everything else emerges. From the churning foam of these interacting geometric quanta, the smooth cosmos of general relativity should crystallize. The physics of the Big Bang should become calculable, and perhaps even the particles and forces of the standard model could be seen as intricate patterns woven into the fundamental geometry of spacetime. The entire universe, in this view, is a condensate of these elementary geometric atoms, a frozen structure in an infinite sea of quantum spatial possibilities. Shape dynamics presents a universe where size itself is relative. This radical new approach reimagines the core of general relativity, trading one profound symmetry for another. Einstein taught us that the laws of physics look the same to all observers regardless of their motion. This is the relativity of locality. Shape dynamics proposes a different, equally fundamental symmetry, the relativity of scale. In this view, the absolute size of an object or the distance between 2 points has no physical meaning. Only the shape of the universe and the angles between objects are real. The physics is described entirely by conformal geometry, the pure study of shape. Think of a balloon as you inflate it. The pattern of continents and oceans changes its size dramatically, but the shapes of those continents, their angles and proportions, remain exactly the same. According to shape dynamics, the universe is like that balloon. The cosmos could be scaled up or down, and as long as its conformal shape is preserved, the physics would be identical. This shifts the entire foundation. Instead of a four-dimensional spacetime metric, the fundamental description of our universe is the evolving, three-dimensional shape of space at each moment. This reframing offers a stunningly simple treatment of time, one of the most vexing problems in quantum gravity. In the standard approach, time is woven into the spacetime fabric, but it becomes a fuzzy concept in the quantum realm. Shape dynamics cleanly separates the background of time from the changing shape of space. Time is what you read on a clock, a simple, measurable interval, while the dynamics of the universe are captured purely by the evolution of spatial shapes. This could resolve deep paradoxes about time's arrow and its role in quantum mechanics. Perhaps most compellingly, this theory finds a surprising echo in our most ancient cosmic light. The pattern of hot and cold spots in the cosmic microwave background, the afterglow of the Big Bang, exhibits a property known as Weyl invariance. This means its statistics look the same on different angular scales, a direct hint that the universe's fundamental laws might not care about absolute size, only about shape. Shape dynamics takes this observational clue and builds a complete gravitational theory upon it, suggesting we have been reading a profound cosmic signature all along without realizing its true meaning. What if time itself is not what we think it is? Horaver Lifshitz gravity dares to ask this profound question, proposing a radical surgery on Einstein's equations to save them from their own quantum inconsistencies. This theory suggests that at the highest energies, at the very precipice of the Planck scale, time and space are not the unified partners we believe them to be. They undergo a dramatic divorce governed by a principle known as anisotropic scaling. Imagine watching a video in extreme fast-forward. The action in time accelerates wildly while the spatial details remain crisp and clear. This is the essence of Lifshitz scaling, where time scales differently from space. To make the theory mathematically well-behaved, time is effectively given more weight, a higher power in the equations. This fundamental asymmetry breaks Lorentz invariance, the sacred principle that the laws of physics look the same to all observers moving at constant speed. For a century, this invariance has been a cornerstone of modern physics, but Horaver Lifshitz gravity posits that it is only an emergent, low-energy illusion. By sacrificing this symmetry at the deepest levels, the theory achieves a monumental goal. It becomes power-counting renormalizable. This means the terrifying infinities that plague standard quantum gravity calculations simply vanish, tamed by the different treatment of time. The gravitational force, once a mathematical monster, becomes predictable and finite at all energy scales. Yet we do not live in this strange, asymmetric world. As the energy of interactions drops to the levels we experience every day, the violent asymmetry between time and space fades away. Lorentz invariance is restored, and the equations smoothly morph into the familiar, tested form of Einstein's general relativity. The fractured relationship heals, giving us back the classical universe we know and love. This elegant fade from high-energy strangeness to low-energy normality has breathtaking consequences. The accelerated expansion of the cosmos, which we currently attribute to a mysterious dark energy, might not need any exotic substance at all. It could be a natural remnant of the universe's early days when time and space were locked in their asymmetric struggle, an imprint left on the cosmos' evolution. Similarly, the missing mass in galaxies, dark matter, might be explained by subtle modifications to gravitational laws that arise from this theory, eliminating the need for an entirely new, undetected particle. Most excitingly, these ideas are not purely philosophical, they are potentially testable. The theory predicts subtle deviations in the behavior of gravitational waves, tiny ripples in spacetime that we can now measure. It could affect how black holes merge or how neutron stars vibrate. As our observatories grow more sensitive, they might detect the faint echo of a universe where time, for a fleeting moment at its birth, played by a completely different set of rules. Two particles separated by a vast cosmic distance can share a mysterious bond. But what if that bond is not a ghostly link but a physical bridge? The ER equals EPR conjecture dares to propose exactly that, weaving together two of the most famous ideas in physics. On one side is the Einstein-Rosen bridge, the elegant wormhole solution from general relativity, a tunnel through spacetime itself. On the other is EPR entanglement, the spooky action at a distance that so troubled Einstein, where the fate of two particles remains inseparably linked. This conjecture declares they are not just analogous, they are one and the same. A pair of entangled particles is not communicating faster than light. They are secretly connected by a microscopic, non-traversable wormhole. The quantum connection we call entanglement is in its heart a geometric phenomenon, a tiny stitch in the fabric of spacetime. This is a profound shift in perspective. It suggests that the bizarre rules of quantum mechanics might have a geometric origin, a hidden architecture built from these microscopic bridges. The implications for unifying gravity and quantum theory are staggering. If every entanglement link is a wormhole, then the entire fabric of spacetime could be a dense, dynamic web of quantum connections. The empty space between stars is not truly empty. It is saturated with these fundamental threads, weaving the cosmos into a single, interconnected whole. This idea offers a radical new perspective on one of physics's greatest puzzles, the black hole information paradox. When something falls into a black hole, does its information vanish forever, violating quantum law? The ER equals EPR picture provides an elegant escape. Imagine two entangled particles, one falling into the black hole and one remaining outside. According to this view, they are connected by a wormhole. The information of the infalling particle is not lost inside the hole. It is preserved in the structure of this geometric link, this entanglement bridge connecting the inside and the outside. The event horizon is not a fiery wall of death, but the point where this complex web of connectivity begins. This directly addresses the firewall controversy, a heated debate about whether an astronaut crossing the event horizon would be incinerated. If spacetime connectivity is built from entanglement, then the horizon is a place of maximum connection, not a violent boundary. The conjecture suggests that destroying the entanglement between the inside and outside of a black hole would not create a firewall. It would sever the wormhole itself, destroying the smooth spacetime geometry and causing the entire black hole structure to collapse. In this breathtaking vision, the universe is not a collection of separate objects in space, but a single, vast network where quantum links and geometric tunnels are fundamentally indistinguishable. Deep within the heart of a black hole, a quantum secret might be hiding in plain sight. The black hole atom hypothesis suggests these cosmic monsters could be structured remarkably like the simplest atom in the universe. Picture a hydrogen atom with a single electron orbiting a central proton. the electron is not free to occupy any random distance. It can only exist on specific quantized energy levels. This theory proposes that a black hole's event horizon behaves in a strikingly similar way. Instead of a smooth, classical surface, the horizon could be quantized, only able to exist in specific, discrete quantum states. The central singularity would act like the proton, the unmoving core, while the horizon itself takes on the role of the electron cloud, a fuzzy, quantum gravitational boundary with a set of allowed configurations. This elegant analogy leads to a profound prediction. Just as hydrogen atoms can only have specific, discrete energies, black holes might not be able to have any arbitrary mass. They would instead possess a discrete mass spectrum, only coming in specific size increments like rungs on a cosmic ladder. This quantum structure of the horizon offers a beautifully natural explanation for a black hole's most famous feature, Hawking radiation. In the standard picture, this radiation is a complex result of quantum fields bleeding energy away from the black hole. But in the atomic model, it becomes as simple as an electron jumping between energy levels. When the black hole transitions from a higher mass state to a lower one, it emits a quantum of energy, a packet of radiation, directly mirroring the photon released when an electron drops to a closer orbit. This approach is a brilliant tactical maneuver in the quest for quantum gravity. It sidesteps the need for a complete, final theory by applying the tried and true principles of atomic physics, which we understand intimately, to the enigmatic quantum properties of black holes. It builds a potential bridge between the impossibly small world of the atom and the impossibly dense world of the singularity, suggesting that the universe may use the same architectural blueprints across vastly different scales. The universe may have crystallized from a formless, blazing network of pure connection. This is the startling vision of quantum gravity, a theory that imagines the vacuum of space not as empty nothingness, but as a dynamic, evolving graph. Its fundamental ingredients are incredibly simple, just abstract nodes connected by links. In the beginning, at the highest conceivable energies, this graph was in a hot, chaotic state. Every node was connected to every other node in a featureless, highly symmetric web. In this primordial condition, the concepts of here and there were meaningless because everything was directly linked to everything else. There was no distance, no direction, and crucially, no dimensionality. The universe was a structureless soup of pure potential connection. Then, as the cosmos expanded and cooled, it underwent a dramatic phase transition, much like water freezing into ice. The overheated graph suddenly found a new, more stable configuration. Countless links were broken, the all-to-all connectivity shattered, and the graph settled into a sparse, regular lattice. From this cosmic freezing, the geometry of our world was born. The specific, limited pattern of connections that remained defined what we now experience as three-dimensional space. The distance between 2 points is not a fundamental property, but simply a measure of how many links you must traverse to get from one node to another. This emergence of geometry from connection is the theory's core miracle, but no crystal freezes perfectly. Just as ice forms cracks and imperfections, the freezing of spacetime graph left behind defects. These are places where the regular, low-energy pattern of connections is disrupted. A node might have a missing link or an extra one, creating a localized kink in the fabric. These imperfections are not flaws, they are the seeds of everything. In quantum gravity, these topological defects in the graph could be the fundamental particles themselves. An electron might be a specific kind of twist in the network, a photon a different vibrational pattern along the links. Matter and energy are not things that live in space, they are the tangled, knotted structures of space. This framework offers a breathtakingly simple origin for some of our universe's most fundamental features. Why are there 3 dimensions of space? The answer could be that this particular lattice structure was the most stable one that formed during the cosmic freeze, the natural crystal of spacetime. Why does Lorentz invariance hold, meaning the speed of light is constant for all observers? This symmetry might not be a fundamental law, but a direct consequence of this underlying graph structure at low energies. As we move through this lattice of connections, its microscopic irregularities could average out, creating the smooth, symmetrical spacetime we observe, just as a speeding bullet perceives a polycrystalline metal as a uniform barrier. The theory suggests that if we could probe spacetime at incredibly high energies, we might see this Lorentz symmetry begin to break down, a faint memory of the universe's hot, connected past. Our reality might run on a cosmic computer. This is the startling proposal of the cellular automaton universe, a theory that envisions existence as a vast computational grid. At its most fundamental level, spacetime is not a smooth continuum but a perfect crystalline lattice of individual cells, like an infinite cosmic chessboard. Each cell possesses only a finite number of possible states, perhaps just on or off, 0 or 1. The entire universe evolves in discrete ticks of a master clock, where every cell updates its state based on a set of simple, local rules. These rules only depend on the states of its immediate neighbors. There is no action at a distance, no global overview, just a mindless, mechanical process where each pixel of reality looks at the pixels next to it and decides what to become in the next moment. From this starkly simple, deterministic foundation, theorists like Stephen Wolfram suggest that all of physics emerges. The frantic probabilities of the quantum world and the smooth curvature of Einsteinian gravity are not fundamental. They are large-scale patterns, intricate behaviors that arise from the collective computation of countless cells following their basic programming. Think of the famous game of life, a simple cellular automaton with just a handful of rules. From those minimal instructions, gliders, oscillators, and even complex self-replicating structures can spontaneously appear. Our universe could be a vastly more sophisticated version of this same principle. The seemingly random decay of a radioactive atom might be the output of a complex, deterministic computation whose inner workings are hidden from our view. The force of gravity could be an emergent consequence of how information propagates across this cosmic lattice, creating the illusion of a curved spacetime. This digital physics perspective offers a radical resolution to the weirdness of quantum probabilities. The famous randomness we observe in particle behavior may not be truly random at all. It could be pseudo-random, the result of deterministic chaos playing out on a scale so fine we cannot perceive the underlying clockwork. This would mean that our universe is ultimately predictable, its entire future written into the initial state and the unbreakable rules of the automaton. The profound implication is that the cosmos is not just described by mathematics, it is mathematics in motion, a computation of literally cosmic proportions. Quantum mechanics has always been haunted by the ghost in the machine, the infamous measurement problem. What actually happens during an observation to make a probability wave collapse into a definite reality? The transactional interpretation offers a dramatic answer, one that paints quantum events not as mysterious collapses, but as a cosmic handshake across time. This picture involves two kinds of waves. The familiar retarded wave moves forward in time from the emitter to a potential absorber, but critically, the absorber also sends a confirmation wave backward in time, an advanced wave that travels from the future to the past. The actualized event, the transaction, occurs only when these two waves match up and reinforce each other, like an echo from the future validating a call from the past. This handshake creates a stable loop in time, and it is within this loop that a particle like an electron is realized, its path from source to detector now firmly established. Now extend this radical idea to the fabric of spacetime itself. What if gravity is not a separate force, but emerges directly from this universal process of transactional handshakes? Every quantum event, every single particle interaction that defines reality, involves this exchange of advanced and retarded waves. The proposal is that this very process of confirmation and realization generates a subtle cumulative stress on the geometry of the universe. This stress could manifest as what we perceive as gravity. In more technical terms, the off-shell gravitons, the virtual particles that would mediate gravity in a quantum field theory, are not free agents. They are the direct consequence of these space-time spanning transactions. They are the geometric glue of the handshake itself. Every time an electron is measured here and now, the advanced wave from its future detector creates a faint, backward-in-time gravitational pull, a tiny warp that is part of the deal. The smooth curvature of spacetime in Einstein's theory would then be the statistical average of trillions upon trillions of these quantum transactions happening every moment, each one a tiny loop in time that slightly warps the stage. This provides a breathtakingly unified solution to two of physics's greatest puzzles. The measurement problem is resolved with a physical mechanism, a handshake with the future. And gravity is naturally incorporated as an inevitable byproduct of that very mechanism. We are not being pulled by masses, but by the accumulated weight of reality itself being continuously negotiated between the past and the future. The graviton stands as the ultimate ghost in the quantum machine, a hypothetical particle that carries the force of gravity. According to the rules of quantum field theory, every force must have a messenger, a gauge boson that transmits its influence. For electromagnetism, it is the photon. For gravity, physicists postulate the graviton. Its required properties are very specific and strange. It must be massless like the photon to ensure gravity's infinite range. But unlike the photon, which has a spin of 1, the graviton must have a spin of 2. This unique spin is what gives gravity its always attractive, never repulsive nature, and it is this very property that makes the mathematics of a simple graviton field theory so fraught with peril. When you try to quantize this spin 2 field using standard methods, the calculations explode into infinities that cannot be tamed, a problem known as non-renormalizability. This mathematical breakdown is not a minor technicality. It is a screaming alarm that our current tools are utterly insufficient, a primary reason why we are forced to consider more radical frameworks like string theory or loop quantum gravity. Yet, even if the math could be fixed, the experimental challenge is staggering. Gravity is astronomically weaker than the other forces. To detect a single graviton directly, you would need a detector so massive and so sensitive it is practically a fantasy. Something like a Jupiter mass sphere of pure lead cooled to near absolute zero, and even then the signal would be dwarfed by the noise of the universe. The weakness is so profound that a single graviton passing through the entire planet would almost certainly leave no trace at all, so why even entertain its existence? Because finding it would change everything. The confirmed detection of a graviton would be the final, triumphant piece of the standard model puzzle, proving once and for all that gravity is indeed a quantum force just like the others. It would validate the entire quantum field theory approach and narrow the search for a final theory dramatically. We would know we are on the right track, that the universe truly does play by the rules of quantized fields and force-carrying particles, even when it comes to the curvature of spacetime itself. The graviton remains the universe's most elusive whisper, a theoretical promise that either confirms our deepest intuitions or forces us to abandon them forever. This deep conflict between our two greatest theories crystallizes in a single, haunting equation. The Wheeler-DeWitt equation is the result of trying to apply the strict rules of quantum mechanics to the entire cosmos, and it presents us with a terrifying picture, a universe frozen solid. In this formulation, time simply vanishes from the equations. There is no variable for now, no operator for later. The wave function of the universe it describes is static, an eternal, unchanging monument. This is the heart of the problem of time. General relativity gave us a dynamic, flexible time that is woven into the fabric of the cosmos, a dimension that curves and stretches. But quantum mechanics requires a rigid, external clock against which the frantic dance of particles is measured. When you try to quantize gravity, these two concepts of time clash violently, and in the Wheeler-DeWitt equation, the classical clock seems to have been shattered. How can we reconcile a fundamental, flowing time with a quantum reality that appears to be timeless? One radical proposal is that time is not real at all. In this timeless picture, the universe just is. Our profound sensation of past, present, and future is a powerful cognitive illusion, a story our brains tell us as we navigate a single, frozen block of reality. Change is not fundamental, it is how we perceive different parts of this eternal structure. Another compelling idea suggests that time emerges from the relationships between things within the universe. Think of a simple pendulum clock. Its ticking is not governed by some external time, but by the relationship between the pendulum's swing and the gears in the mechanism. In the same way, cosmic time might be a derived concept. The flow we experience could be generated by the changing correlations between physical variables. For instance, the expansion of the universe itself could serve as a master clock. The growth of space provides a sequence against which all other processes can be measured, making time a story told by the universe's contents to each other. A more modern approach finds the origin of time in information and its inevitable blurring. When we look at a complex quantum system, we can never know every microscopic detail. This act of coarse graining, of ignoring the finest quantum information, may be what creates the arrow of time. It is the thermodynamic gradient of the cosmos, the progression from a more ordered to a more disordered state of information, that gives us the unidirectional flow we experience. From this perspective, time is the manifestation of our ignorance, a fundamental fuzziness in our description of the world. Each of these proposals grapples with the same profound puzzle, trying to rescue the vivid reality of our experience from a mathematical formalism that seems to deny its very existence. The problem of time forces us to ask whether our most basic intuition about reality is a local effect, a beautiful and necessary consequence of our place within a much larger and possibly timeless whole. The quiet emptiness of space is not empty at all. It seethes with a violent temporary energy, a quantum foam where particle-antiparticle pairs flicker in and out of existence in a frantic dance. According to quantum field theory, this vacuum should be screaming with an immense energy density, a repulsive force of such staggering power that it should have ripped the universe apart in its first instant. This is the predicted value of the cosmological constant, the engine of dark energy. Yet when we look at the cosmos, we see a universe expanding at a gentle, accelerating pace. The observed energy of the vacuum is not just a little smaller than the prediction, it is smaller by a factor of 1 followed by 120 zeros. This is not a minor oversight, it is the most spectacular failure of a prediction in the entire history of science. The cosmological constant problem is a direct and brutal clash between gravity and the quantum world, a screaming mismatch that reveals our fundamental theories are missing a crucial piece. The problem is one of coupling. General relativity tells us that all forms of energy curve spacetime and produce gravity. The quantum vacuum, with its unimaginably huge energy, should therefore generate an immense gravitational repulsion. The fact that we don't see it means that somehow the gravitational effect of the quantum vacuum is almost perfectly cancelled out, leaving only the tiny, leftover whisper we call dark energy. Solving this is a core task for any theory of quantum gravity, as it must explain how gravity couples to the quantum vacuum in such an unnaturally precise way. String theory approaches this through the concept of the landscape. It suggests our universe is just one of an astronomical number of possible vacuum states, each with a different value for the cosmological constant. In almost all of these universes, the constant is huge and the cosmos tears itself apart instantly. we, of course, find ourselves in one of the incredibly rare, finely tuned pockets where the constant is minuscule, allowing for galaxies, stars, and life to form. This anthropic reasoning is controversial as it shifts the question from a calculation to a selection effect. The idea of asymptotic safety offers a more deterministic path. It proposes that the gravitational fixed point, that anchor of stability, forces the cosmological constant to flow to a very small, non-zero value at the low energies we experience. The constant is not fine-tuned. It is mathematically inevitable within a fully consistent quantum theory of gravity. Other ideas suggest a yet unknown symmetry that forces the vacuum energy to be zero, with dark energy arising from an entirely different source, or that the quantum vacuum's energy simply does not gravitate in the way we assume. Each attempt to solve this problem forces us to confront the deepest nature of reality, questioning whether our universe is one lucky ticket in a cosmic lottery, or if a deeper law is at work, patiently holding back the storm of nothingness to let something exist. A dying black hole presents quantum physics with its most terrifying puzzle. Stephen Hawking's brilliant calculations showed that black holes are not truly black. They slowly evaporate by emitting a faint glow of radiation. But this Hawking radiation, pulled from the vacuum near the event horizon, is entirely random, carrying no information about the star that collapsed or the books you might have foolishly thrown in. When the black hole finally vanishes, all that intricate information seems to be erased from the universe forever. This violates a sacred principle of quantum mechanics called unitarity, which states that information can never be truly lost, only scrambled and rearranged. For decades, this information paradox suggested our most fundamental laws of physics were incomplete, that a choice had to be made between Einstein's gravity and quantum theory. Solving this paradox has become the ultimate proving ground for every theory of quantum gravity. Each approach attacks the problem from a different angle, defending the sanctity of information. String theory, through the AD/CFT correspondence, provides a powerful answer. Remember the holographic universe, where a gravitational bulk is dual to a quantum theory on its boundary. In this picture, a black hole forming and evaporating in the bulk is perfectly described by a complex but perfectly unitary process on the boundary. The information never falls into a pit of no return. It is merely transformed and encoded in the thermalized state of the boundary quantum system. It is always preserved, just in a language we are only beginning to decipher. Loop quantum gravity tackles the issue by redefining the black hole's very structure. Its calculations of black hole entropy, counting the number of distinct ways the horizon's quantum geometry can be configured, show that the horizon is not a simple surface. It is a vibrant quantum layer rich with information. As the black hole evaporates, this information is not carried away by the Hawking radiation itself, but is imprinted onto the correlations between the early and late particles of the radiation. To retrieve the information of what fell in, you would need to collect all the radiation the black hole ever emitted and perform a monstrously complex quantum calculation on the entire set. The information was never lost. It was delocalized across the entire radiation field. The most mind-bending recent development comes from a blend of holographic ideas, introducing the concept of entanglement islands and replica wormholes. This suggests that as a black hole ages, regions in its interior, far behind the event horizon, become quantum entangled with the radiation streaming away into space. These interior zones, the islands, are not causally connected to the outside, yet their information is somehow accessible through the radiation. It is as if the information has two addresses at once, both deep inside the black hole and also smeared across the distant Hawking radiation. The replica wormholes are the geometric bridges that allow this paradoxical duplication to be consistent, saving the quantum rules without creating a logical nightmare. The event horizon, in this view, is not a firewall but a computational surface. a place where the universe performs a cosmic sleight of hand to preserve its own logical consistency. The fate of a single qubit of information falling into a black hole is no longer a mystery but a stringent test, a challenge that every candidate for a final theory must pass to prove it holds a piece of the ultimate truth. String theory offers a universe of possibilities, a near infinity of them. This is the concept of the landscape, a vast, abstract terrain where every point represents a different possible vacuum state for reality. Each of these valleys in the landscape corresponds to a universe with a unique set of physical laws, different particle masses, varied force strengths, and even a different number of spatial dimensions. In this cosmic garden, the number of possible stable configurations is astronomically large, perhaps as many as 10 to the 500 different versions of physics. Our universe, with its specific values for the cosmological constant and the mass of the electron, is just one tiny, fertile patch in an endless wilderness of possibilities. This immense diversity leads to a profound, and for some, a deeply unsettling explanation for why our constant seems so finely tuned for life. It is anthropic reasoning. In a multiverse of infinite variety, we obviously find ourselves in one of the rare universes capable of supporting conscious observers. The laws are not fine-tuned for us. We are simply the inevitable product of a selection bias, living in one of the few places where life could ever ask the question. Yet for physicists seeking a single, unique theory of everything, the landscape can feel like a disappointment, a surrender to cosmic chance. From this tension, a powerful new idea has emerged: the swampland program. This is not a collection of theories, but a set of sharp criteria, a litmus test designed to separate the true landscape from the swampland. The swampland consists of all those seemingly consistent effective field theories that look good on paper, but which can never be successfully coupled to a full theory of quantum gravity like string theory. They are mathematical mirages, theories stuck in the mud, unable to connect to the solid ground of a quantum gravitational reality. The program proposes clear conjectures to identify these dead ends. One of the most influential is the distance conjecture. It suggests that as you move an infinite distance in the field space of a theory, an infinite tower of new, ultra-light particles must appear, their masses dropping to zero. This effectively prevents you from ever reaching a true limit where a dimension decompactifies or a coupling constant becomes infinite, because the theory fundamentally changes before you get there. Another key idea is the de Sitter conjecture, which casts doubt on the long-term stability of a universe like ours, with a small, positive cosmological constant driving accelerated expansion. It proposes that such a vacuum might be inherently unstable in a full theory of quantum gravity, destined to decay. These are not just abstract mathematical games, they are making concrete, testable predictions for cosmology. If the de Sitter conjecture holds, our current era of dark energy-driven expansion may not be eternal, but a transient state on the verge of collapsing into a new phase. The properties of the elusive dark energy we measure could be a direct reflection of these fundamental constraints, a sign that we are not in the swampland but on the firm ground of the landscape. This ongoing battle between the fertile landscape and the treacherous swampland is reshaping the quest for quantum gravity, forcing theorists to ask not what is mathematically possible, but what is gravitationally mandatory. The violent beginning of our cosmos might not have been a beginning at all. Quantum gravity theories are rewriting the story of the Big Bang, transforming it from a singular, inexplicable moment into a physical process we can hope to understand. In the very first instance, when the entire universe was compressed into a volume smaller than a single atom, the quantum nature of gravity would have been the dominant force, overriding the classical equations that break down. This is the realm of quantum cosmology, where our most ambitious theories are applied to the entire universe in its infancy. Loop quantum cosmology, for instance, paints a stunning picture. It suggests that the Big Bang was not a true singularity, but a tremendous rebound, a great bounce from a previous cosmic phase. Before our expanding universe, there was a vast, contracting one, collapsing under its own gravity. But instead of crushing itself into an infinitely dense point, the quantum geometry of space reached a maximum possible compression. The repulsive force generated by this quantum pressure became so powerful that it overcame gravity, forcing the universe to bounce back and initiate the expansion we see today. Our entire cosmic history could be one cycle in an endless series of expansions and contractions, a cosmic heartbeat echoing through eternity. String gas cosmology offers a different vision of the initial state, drawn from the principles of string theory. Imagine the very early universe as a hot, dense, and compact space, with all 9 or 10 spatial dimensions curled up tightly. The fundamental strings that make up reality would have been wound around these compact dimensions, vibrating and colliding in a frenetic soup. As the universe cooled, a pivotal phase transition occurred. Only 3 of those spatial dimensions were destined to expand, unfurling to become the vast stage we inhabit. The rest remained tightly wound, hidden from our perception at microscopic scales. In this model, the large-scale uniformity of the cosmos, a major puzzle in standard cosmology, arises naturally from the thermal equilibrium of this early string gas. The strings interacted and reached a uniform temperature, smoothing out the universe before the great expansion began. These are not just beautiful stories, they are scientific models that make predictions. The quantum gravitational ripples from that first moment could have left faint scars on the cosmos, imprints we might still detect today. The cosmic microwave background, the afterglow of the Big Bang, is our most powerful window into this primordial era. Certain subtle patterns in its polarization, a specific swirling signature known as primordial B modes, could be the direct fingerprint of gravitational waves generated during an inflationary epoch driven by quantum gravity. Furthermore, the detailed spectrum of temperature variations across this ancient light could reveal a characteristic graininess, a slight deviation from perfect scale invariance that points directly to the discrete structure of spacetime predicted by theories like loop quantum gravity. Even the faintest hum of a primordial gravitational wave background, a relic signal washing through the universe, might carry the unmistakable signature of a bounce or a string-driven genesis. Finding these signals is the monumental goal of next-generation observatories. They are hunting for the ultimate cosmic artifact, a message in a bottle from the moment time itself began, written in the subtle language of quantum gravity. These beautiful theories remain trapped in the realm of pure mathematics until we can find a way to test them. The central challenge is one of scale. To directly probe the quantum grain of spacetime, we would need a particle accelerator the size of our galaxy, capable of reaching the unimaginable Planck energy. Since building such a machine is impossible, physicists have become cosmic detectives, searching for subtle clues left behind by quantum gravity in the universe around us. One of the most promising crime scenes is the cosmic microwave background. This ancient light, the afterglow of the Big Bang, has traveled across the cosmos for over 13 billion years. During its epic journey, the polarization and temperature of these photons may have been subtly twisted by the primordial quantum foam. Certain patterns, like a specific type of swirling in the polarization known as primordial B modes, could be the direct fingerprint of gravitational waves generated when the universe was smaller than an atom. Finding this signature would be like discovering the first brushstroke on the canvas of creation. Meanwhile, the new era of gravitational wave astronomy offers another powerful lens. When 2 black holes or neutron stars spiral together and merge, they shake the very fabric of spacetime, sending out ripples we can now detect. By comparing the intricate details of these signals to the predictions of general relativity, we might spot tiny deviations. Perhaps the waves ring down differently, or their propagation speed changes at extremely high frequencies. hinting at a discrete spacetime structure or a violation of Lorentz invariance at the smallest scales. These cosmic messengers carry secrets from the most violent events in the universe, and they might just be whispering the laws of quantum gravity. Scientists are also looking at ultra-high energy cosmic rays, particles that arrive from deep space with energies far beyond what our colliders can produce. If spacetime has a fundamental graininess, these tremendously energetic particles should interact with it, perhaps traveling at slightly different speeds depending on their energy. We have even begun to bring the cosmos into the laboratory through ingenious analog experiments. Certain exotic states of matter, like Bose-Einstein condensates or superfluid helium, can be manipulated to create environments where sound waves behave exactly like light waves in a curved spacetime. These sonic black holes, or analog gravity systems, allow us to study the analog of Hawking radiation in a tabletop experiment, providing tangible insights into how quantum effects and geometry can intertwine. The quest is no longer purely theoretical. We are building the tools to listen to the faint hum of spacetime itself, turning the deepest questions of philosophy into problems of observational science. Information itself may be the final ingredient in the cosmic recipe. The profound connection between quantum information and spacetime geometry is revolutionizing our approach to quantum gravity, suggesting that the universe is not just described by information but might be built from it. This starts with a deep link forged by entanglement. In the holographic universe, the amount of quantum entanglement between a region of space and its surroundings is not an abstract number. It directly determines the geometry of that region. The Ryu-Takenogi formula provides the stunningly precise dictionary. It states that the entanglement entropy of a quantum system on the boundary is exactly proportional to the area of a minimal surface extending into the higher dimensional bulk. More entanglement on the boundary does not create more volume inside. It literally creates more surface area, warping the geometry from the outside in. This means the very connectivity of space, the fact that you can move from one point to another, is woven from the invisible threads of quantum entanglement. But entanglement is just the beginning of the story. Dive deeper into a black hole and you encounter an even more mysterious property: quantum computational complexity. This measures how difficult it is to construct a particular quantum state from a simple starting point. As time passes inside an old black hole, its internal quantum state becomes exponentially more complex. At the same time, according to the holographic description, a fascinating geometric transformation is occurring deep within the black hole's interior. A wormhole, an Einstein-Rosen bridge, is growing longer and more intricate. The astonishing proposal is that these two processes are one and the same. The growth of the wormhole, a purely geometric phenomenon, is exactly equivalent to the increase in the quantum computational complexity of the state describing the black hole. The bridge is not built from steel or stone, but from complexity itself. This radical idea suggests that the interior of a black hole is not a place in the traditional sense, but a physical manifestation of an incredibly complex quantum calculation. The most practical application of this quantum information perspective may lie in error correction. The holographic universe seems to employ a cosmic version of the codes we use to protect quantum computers from decoherence. In a quantum error-correcting code, information is not stored in one fragile location. It is delocalized, spread out, and hidden within the correlations between many different qubits. To read the information, you cannot just look at one piece, you must consult nearly the entire system. This is exactly how information appears to be stored in the holographic description of spacetime. A single particle in the bulk of the universe is not a localized dot. It is a logical construction, its existence encoded across a vast network of entangled degrees of freedom on the distant boundary. The particle exists here in our three-dimensional world only because of a flawless error correction routine running on the cosmic screen. this implies an incredible fragility to reality. If you could somehow destroy a large portion of the boundary, you would not just lose a part of the universe, you would corrupt the error-correcting code itself, causing entire regions of space to literally disappear from existence as the information storing them becomes unrecoverable. The universe, in this breathtaking view, is the ultimate quantum computer, and the stable spacetime we experience is its fault-tolerant operating system, running smoothly against a constant background of quantum noise. What if dark matter is not missing matter but missing physics? For decades, the unexpected speed of stars orbiting the edges of galaxies has been explained by an invisible, mysterious substance that outweighs all visible matter 5-1. Yet another idea proposes a far simpler solution, that our understanding of gravity itself is subtly incomplete on the vast, diffuse scales of galactic outskirts. This is the radical proposition of modified Newtonian dynamics, or MND. It is not a quantum gravity theory itself, but a stunningly successful phenomenological model. MND introduces a simple new constant of nature, a tiny but critical acceleration threshold. Above this threshold, in regions of strong gravity like our solar system, Newton's and Einstein's laws reign supreme. But below this threshold, in the extremely weak gravitational fields at the fringes of galaxies, the force of gravity begins to behave differently, strengthening slightly to hold fast-moving stars in their orbits without any need for dark matter. The predictive power of this simple adjustment is breathtaking. It accurately forecasts the rotation curves of a vast array of galaxies from a single measurement of their visible mass, a feat the dark matter paradigm struggles to match without carefully tuning the distribution of this invisible stuff for each individual galaxy. To make this idea compatible with Einstein's relativistic framework, theorists developed more complete theories like tensor vector scalar gravity, or TVS. This framework adds new fields to the fabric of spacetime, a scalar field that tweaks the overall gravitational potential and a vector field that picks out a preferred direction in time. Together, these fields modify how gravity acts in the weak field limit, successfully reproducing MND behavior and even predicting subtle new effects in gravitational lensing, the bending of light by gravity. The ultimate dream, however, is that a final theory of quantum gravity might naturally explain why MND works so well. Could the microscopic quantum structure of spacetime somehow produce this specific modification to gravity on galactic scales? Perhaps the collective behavior of spacetime's fundamental atoms, whether they are loops, strings, or quantum bits, generates an effective force law that mimics MND in the low acceleration regime. This would be a monumental unification, solving two of cosmology's greatest puzzles with one elegant stroke. A fundamental theory would not just quantize gravity, it would reveal why gravity appears to change its character on different scales, rendering the immense, invisible halo of dark matter redundant. The success of MND stands as a persistent, data-driven challenge to the foundations of physics, a clue that the quantum nature of gravity might be hiding in plain sight, written in the silent, swirling dance of distant stars. A single equation, elegant and profound, might one day describe the entire cosmos. This is the ultimate dream of unification, a final theory that would not only tame gravity but weave it seamlessly into the fabric of all other forces and particles. Such a framework would reveal the universe not as a collection of separate phenomena, but as the inevitable consequence of one beautiful, underlying principle. From the frantic dance of quarks to the majestic swirl of galaxies, everything would spring from the same source. But is this dream of a theory of everything even a coherent goal, or are we chasing a phantom? Different paths offer starkly different answers. String theory pursues a kind of mathematical uniqueness, a single master theory from which all other string theories are born, hoping to find one unique description with no free parameters. Loop quantum gravity, in contrast, builds reality from the bottom up, focusing on the quantum nature of space itself, suggesting that the Standard Model and its forces might emerge from the geometry of spin networks. The radical approach of emergent gravity questions the very premise, arguing that there is no quantum theory of gravity to find because gravity was never fundamental to begin with. It would be a collective behavior, an outcome, not a force to be quantized. If one of these paths proves successful, the implications would shatter our current understanding. A true theory of everything would not be the end of physics, but a magnificent new beginning. It would provide the fundamental rules, the cosmic constitution, from which the entire history of our universe could, in principle, be derived. We would possess the key to the first moment of time, understanding the precise conditions of the Big Bang and the origin of the cosmos itself. It could finally explain the seemingly arbitrary numbers that define our reality, like the mass of the electron or the strength of the gravitational force, revealing whether they are the only possible values or just one outcome in a vast multiverse. The search for this final theory is more than a technical challenge. It is a quest to discover if the universe is ultimately simple, elegant, and comprehensible, a silent mathematical harmony waiting to be heard. Our search for quantum gravity is far more than a technical puzzle. It is a journey to the very bedrock of what we call reality. Each theory we have explored forces us to question our most basic assumptions. If spacetime is emergent, then what we perceive as the immutable stage of the cosmos is a grand illusion. The flow of time, the very sensation of now slipping into then, could be a thermodynamic artifact, a story written by our own limited perspective as complex systems within a possibly timeless whole. This suggests a universe that simply is, a frozen block where past, present, and future coexist with equal reality, and our conscious journey through it is a beautiful, necessary fiction. The concept of a beginning itself dissolves. Asking what happened before the Big Bang becomes as meaningful as asking what is north of the North Pole. In a bouncing universe or a cyclical cosmology, our cosmic genesis was not a singular creation from nothing, but a transition from a prior state of existence, one governed by the same quantum gravitational law. This challenges the principle of causality, the idea that cause must always precede effect. In a timeless, quantum geometric reality, the relationships between events might be fundamental, while the arrow of time is a secondary, emergent property. Perhaps the universe is not just described by mathematics, but is mathematics in its most profound and self-aware form. The particles, forces, and the space-time they inhabit could be the physical expression of an eternal, logical structure. This Platonic view finds a partner in the computational universe hypothesis, where reality is the output of a deterministic or quantum algorithm running on a cosmic scale. This leads us to the most haunting question of all, the role of the observer. Quantum mechanics has long grappled with the measurement problem, the strange dependence of a quantum system on being observed. If consciousness is somehow required to collapse probability waves into definite reality, what does that mean in a quantum gravitational context, especially one where time is not fundamental? Is the universe waiting for a conscious observer to bring its entire history into being? Or is consciousness itself an emergent property of a specific, complex quantum gravitational state? Solving quantum gravity is not merely about finding an equation that works. It is about discovering what kind of place we actually live in. Are we temporary patterns in an eternal mathematical landscape, or are we participants in a cosmic process of observation that gives reality its shape? The answer will not just complete our textbook, it will redefine our place in the cosmos, telling us whether we are inhabitants of a universe or whether the universe, in some deep and mysterious way, is an expression of us. From the delicate vibrations of cosmic strings to the granular atoms of space in a spin network, this journey through 30 theories reveals a cosmos of breathtaking possibility. We have wandered through holographic worlds where reality is a projection, explored universes where gravity is a thermodynamic mirage, and witnessed the birth of spacetime from the simple logic of cause and effect. Each framework, from the mathematical elegance of twistor theory to the stark digitality of a cellular automaton, is a testament to human creativity, a different lens through which we strive to decipher the universe's deepest code. This grand quest to unite the infinitely large with the infinitely small is more than a scientific problem. It is one of the most profound intellectual adventures ever undertaken, stretching the very fabric of human thought to its limits. The very fact that we can conceive of these realities, that we can use mathematics to probe a realm 1 billion times smaller than an atomic nucleus, is a triumph of curiosity. The final chapter of this story has not yet been written. The true nature of quantum gravity remains hidden, a secret the cosmos is still keeping. This means the universe is far stranger, more complex, and more wonderful than our everyday experience suggests. So we leave you with this challenge. Which of these visions resonates most deeply with you? Does the holographic principle captivate your imagination, or does the elegant emergence of gravity from pure information feel more compelling? Share your favorite theory in the comments below. Join the conversation with fellow cosmic explorers. If you want to continue this journey of wonder, subscribe for more deep dives into the mysteries of existence. Never stop asking questions, never stop looking up at the stars and wondering what incredible truths are still waiting.